Hello, this is the assistant to Dr. Snidely, and I'm curious if today I may call him in his holiday saying that the total domination is achieved. To do that, I'd first want to do some benchmarking here. Right now for us it's 0.427 seconds for a 1024 by 1024 image with one sample, so no oversampling at all, which is pretty decent. Well, 0.42 seconds, but yeah. Doesn't really matter. Go takes much longer. It's like 3 times slower by default. In 1.2 seconds it does what it does. But Go has this one advantage. It can use multi-threading. So let's set CPUs to 8 and there you go. Go has beaten us. 0.26 seconds, even though it needed 8 cores to do that. And with 3 cores it's kind of as fast as us. And with 2 cores, it's slower again. Well, that was expected. But yeah, let's go to multi-threading. We need multi-threading too. Shouldn't be too difficult, right? Alright, let's first think about what's needed here. Right now we are writing each pixel, which is supposed to be in sequence. So we have this pixel writer type that just has a function called a method called writeNextPixel, which is fine as long as everything comes in order, but that's not gonna happen anymore in the moment we work with threads, because multiple threads are active at the same time producing pixels in different regions of the image. So about parallelization, maybe it's great in our case because we have an image and we can easily subdivide it into multiple sub-regions and then say, okay, thread 1 renders that region, thread 2 renders that region, or something like that. Fair enough. But this definitely means we have to revise the way we will take or write the individual pixels that are being produced. For that, I think it's easiest to have a buffer, some sort of buffer that keeps the memory with itself for a certain region in the image. So it's like a buffer that knows where it is in absolute space. That way, we can basically subdivide the image into multiple of these RGBA buffers and then send these over to the respective thread for processing. It's quite important to not try to share an underlying image buffer that is big enough to hold the entire image, because Rust would give us a hard time to do that. After all, it's a shared resource and threads and shared resources don't like each other so much. So in order to keep it safe, you'll make sure that each thread gets its own little region of the final image, which is exclusively owned by the respective thread. One of the primary methods of the RGBA buffer is setPixel from float, which is used by the threads which actually produced a pixel. So the idea is that setPixel from float is only used for the little sub-regions that are handled by one thread at a time. When the final result is supposed to be aggregated, we need yet another function, which is setPixels from buffer. That way, the individual subregion can easily be written into the full image pixel buffer that is held by someone who keeps or aggregates all the results. Oh, and how could I possibly forget? The vector hassle. Alright, so we have this RGBA buffer and it's initialized with a certain image region, right? But for that it needs to locate the memory required to hold all the pixels which are stored in RGBA. So it's 4 components per pixel, RGB and alpha, all in U8. That's simple. And of course it's kind of straightforward to just store it in a single vector that has basically the area of the rectangle times the number of, well, you see it there. It's exactly that formula used to compute the total size. But what I don't want, or what I do want, is to initialize the entire memory with 0. And as Rust uses RAII, resource allocation is initialization, I am sure that the buffer it allocates is naturally initialized with all zeros. But unfortunately, I was kind of unable to easily create a vector that has a given length without having me or without forcing me to push everything. It took me a long time to, look through source code just to see that the current implementations seem to be inefficient. So if I would use iterators and collect, like repeat 0, take 1000, collect, it will generate a vector. But it has been created using like a terzillion function calls that are just not necessary. Terrible. I mean, really, is that it? So what I had to do is to resolve to an unsafe function, just because there is no with reserve or with capacity. Yeah, it's not that with length, you know. I want a vector function that is with length, so that I can get a vector that is initialized maybe to a certain default value that I can provide as well, and that has a certain length already, so I can access each member without triggering an issue there. But yeah, that didn't happen. So it's with capacity and then unsafe. Set length to get that done. I mean, it's supposed to be fast, right? Don't want to waste cycles for something as simple as this. So I think that is something we could possibly improve in our Rustacean society at some point in the future. It takes a little while to adjust all the interfaces that are involved in that, just to see if we can actually write the same image that we could write previously, all in single-threaded mode. So here it is. And ooh, that looks suspiciously like something that is correct, but it's only magically 1/4 of the image. What could that possibly be? I'm thinking for a long time there. And because old me is a bit stupid sometimes, I decided to first test what it could be. So if I flip the y-axis, do I see something else then? Which is what I would expect. And yeah, let's see what that ends up being. Yeah, that could be it. Maybe is that the inverse of what I want to do here? Yeah. Let's make sure we don't have an out-of-bound issue there, which of course Rust would tell us about. And now let's go for it. Is it something else? Wow, it's actually the first time that we rendered a flipped or correctly flipped image, but it's still just magically 1/4. So think even harder. Think even harder, Mr. Assistant. It's getting warmer. It's getting much warmer. If you look at this, you will see that the copying of pixels from one buffer to another doesn't account for the fact that, in fact, we have 4 components there, right? But the components are nowhere to be found. This is why exactly 1/4 of the pixels were copied, but not the rest. Quite an interesting one here. So with that in place, I believe we should be back to normal and then can take full care of the actual multi-threading. An entire lifetime later, I find myself at a spot where in theory everything should just work, at least should do something, if there wasn't the lifetime check. Okay, let's recap. Right now in Rust, and that's kind of the lesson learned here, everything you pass to a thread must either be owned by the thread, or if it's some reference type, it must have the static lifetime. And guess what? Static lifetime is something you cannot achieve with anything that is located on the stack at all. Therefore, something that is passed to the thread must be on the heap. That's it. There's no other way. And this is something that took me a while to realize, and I kind of started to make methods static, or basically make them type methods so that there's no instance involved anymore, which in turn is located on the stack, which is the right thing to do, definitely. But at the end, there was always the scene which came from stack allocation. I mean, stack allocation, sure, lots of stuff that the scene contains, the geometry is in vectors, and these allocate something on the heap. So in a way, it's not entirely on the stack, but the main bit was. So that's kind of the thing that has to be fixed, and that shall be done right now. Right now, clearly in the sense of right after a little intermezzo. Even though that line is going to move elsewhere, it still shows kind of the basic idea of me getting an environment variable that is in turn interpreted or parsed into an integer. And it's totally right, you know, Rust forces you to make things safe. You kind of have no other way to, or you have no real way to make things unsafe unless you hack around. So what you see here is me getting an environment variable, which is basically returning a result. So I'm dropping any error and say, good, give me whatever you have there, which returns an optional, which I then unwrap, or if there is nothing to unwrap, I shall return a default value 1. And as 1 is a static string slice, I have to convert it to a string in order to be whatever we would expect from varstring. And then whatever comes out of there, we parse as usize, and that returns a result, which, you know, I don't care about the error. So if there is an OK, I unwrap it, or I default to a actual integer 1. Wow. That is kind of something, even though I like it, honestly. I like it because, yeah, that's how it is. The more remote the data source is, the more difficult it is for you to access that, because lots of stuff can go wrong and you have to check it. And honestly, if you look at that, that doesn't look bad at all. I mean, it's kind of readable, and yes, that's safe code. I know this is definitely doing the right thing in all cases. Awesome. And now we are quite close to actually doing this. The only thing missing here is the scene that is supposed to be heap allocated. So what we need is an atomic reference counted instance of our scene here. And this is how it's done, really easy and straightforward. And then what we do is pass a clone of that reference to our function, even though we could also just use a reference there. I mean, who cares really? It doesn't matter if there's one refcon more or less. And just to final cut later, we're actually at a spot where we can try our new rtrace maxprox environment variable 0 threats. That's not gonna work, so there is an assertion triggered, which was put in there by the Rust developers. Good. Nothing else is expected. And with 4 processes, we are about a bit less than 4 times faster, and with 8 cores, 0.116. Well, that is pretty much what can be expected on an actual quad-core CPU that has additional 4 logical cores. So yeah, let's try that again with more samples. That is about right, I suppose. So much faster than it would have been in any other case, but with higher quality. That's quite awesome. The last thing is this bloody flippin' y-axis that actually is flipped, and I think that should just be done next. The easiest way to do this for us is by just inverting the y-axis at the spot where we create the direction of the ray that we want to shoot at a particular pixel. So as you can see, I just do my typical subtraction, and with 8 cores, high performance rendering later. Well, that was too quick, but anyway, nothing to see here. Move along, move along. You see that now finally the image is looking exactly as it's supposed to be. Awesome, terrific. I'm very happy. To be honest, I would have to call Mr. Snidely, Dr. Snidely, and maybe the captain as well, because we are quite ready now. But I think I'll just leave this to the next phase when, you know, just to make sure that everything is pretty, and maybe we want to be prettier than that, right? We are fast, we are close to total domination, but I think we should also be the prettiest RaySpheres producer around the universe. So let's do that in the upcoming phase.
That and more in our next episode of Trace Quest 5.